record and start to share screen. This one. Okay, so today we will start with a new topic. Okay, so today we will start with a new learning model. It's called KNN. So over here, the full name is K nearest neighbors, okay? And it's an unsupervised learning, okay? Previously, the models that we learn is supervised learning. Hold on, okay, let me admit the more. To minimize this. Okay. And then I need to move on to the next one. So that's the name of this new learning model. And just remember, it's unsupervised learning. Okay, and here's some brief description about K nearest neighbor. Okay, and it says it's a lazy learner. And it doesn't learn discriminative function from the training data, okay, but to memorize the training data set. So if you recall previously, a number of the learning models that we learned is it, so it's regarding like a gradient descent, it's regarding cost function. So try to minimize cost function. And for decision tree, random forest, that we try to have maximize information gain. So that's so over there it learns some discriminative function, is it? But for KNN it's different. It's a lazy learner, okay? So it doesn't learn a discriminative function, so we don't have a cost function, okay, or some information gain to calculate. But it says it's memorize the training data set instead. So what does that mean? Okay, so let's take a further look. Okay, so generally speaking, the algorithm, how it works, you will see it's quite straightforward. Okay, this says choose the number of K. So K is the number of neighbors and a distance metric. So that's the first step. So here K, this K is number of neighbors. Okay, so what this means is, so you have the data set, is it? And you choose some sample, is it? And then you are going to find its neighbors. So that means that's its neighbors, K neighbors, okay? And then it says find K nearest neighbor. So based on certain distance metric, you define, okay, you're going to find the K nearest neighbors of the sample that we're still going to do classification, okay, classify. And then you assign class label by majority vote. So here the key point is you're going to find the neighbors, then based on the neighbors class, and you're going to assign the class based on majority vote. Okay, so that's the key concept here. That's how the algorithm works, and we can see it's quite straightforward, is it? So here we have this diagram shows. So for the diagrams, it shows is it, so you have, over here we have three class. Is it, we have circle, we have cross, and we have triangle, is it? And like in this diagram shows, so you have this question mark sample, is it? And you don't know what its class is it? So then over here we said, okay, the K is 5. So we are going to choose 5 neighbors and the nearest. And this nearest definition is based on the distance that you define, okay? And then you choose 5 neighbors. Then you are going to see what are their classes are. So over here you have 3 triangles, 1 circle and 1 cross. And then the majority vote. So in this case, because you have 3 triangle class, is it? So this definitely is more than the circle and the cross, is it? So by majority vote rule, then this question mark, so you're going to predict the class is triangle. Okay, so that's the basic idea about K nearest neighbor, okay? So you can see the idea is quite straightforward. Okay, then let's see. So over here states the advantage of the nearest K nearest neighbor. It doesn't need, as previously we saw, it doesn't need any discriminative function, the cost function, information gain. No, it doesn't need it. But you can see because it choose neighbors and then do classification. So it is a memory-based approach, is it? And here says the classify immediately can adapt as you collect new training data. So this is different from what we learned before. So this is a memory-based, is it? And the downside then for this memory-based approach is its computational complexity of classifying new sample. It grows because with the number of samples growing, is it? Then the computation complexity is also growing, is it? So it says in the worst scenario, is it? Unless it says the data has very few dimensions, is it? So that means few features. Okay, so here we use dimensions and features, is it? Or the data has already been structured as certain efficient data structure, is it? So this is the downside, the computational complexity grows a lot, okay? And furthermore, it says we cannot discuss the training samples, okay? Because no training step is involved and it needs a lot of storage space, okay? Because it's memory-based, so the storage space, it plays also an important role here. So this is the K nearest neighbor classification's advantage, disadvantage, okay. And some other points about the KNN is the number of neighbors, okay. So what's the optimal number? So this is also crucial, okay. Because we need to find a good balance, is it between overfitting and underfitting, okay? And just remember for our machine learning that the overfitting, underfitting, we needed to deal with. That's previously we learned as a regularization is one way to do it, is it? But just think about where regularization work for KNN. It's not, is it? Because regularization try to deal with in cost function, try to deal with that lambda, is it? and you add the regularization term. So over here, we don't have discriminative functions, so this won't work. So how do we deal with overfitting and underfitting later on? We can see, okay, we will see. And also the right distance metric, because you're going to choose the nearest neighbor. So what kind of distance definition you're going to choose? Here it says sometimes it's simple Euclidean distance, and but there are some other times that won't work, so there are different distance metrics that you can also choose, okay? And here it also says, if you choose Euclidean distance, also remember to standardize data, okay? So that each feature contribute equally to the distance, okay? So previously, we also learned that in gradient descent, that we also try to do the feature, we call it feature standardization, or normalization. So that's with data pre-processing, so that you can bring all of the features to the same scale. That you remember the example is like of a house. House, the square foot, versus number of rooms. Definitely not in the same scale. So when you do the gradient descent training, it won't work well. But if you bring all the data to the same scale, that will work more efficient. So that's why over here, because you're going to use distance matrix, so similar, you need to standardize the data, okay, to scale the data. Okay, so this is just some side notes. And then, so next we discuss about the distance matrix. Okay, distance matrix. And over here the mention is called Minkowski distance. Okay, so it says Minkowski distance is a generalization of Euclidean distance, Manhattan distance. It says it can be written like in this format. Okay, in this format. So the distance, the distance between 2 points, between 2 points. And over here, you need to consider all of the features, because for each sample, it has more than one feature. So you can power to P, and then you can do the root key, So over here, then if P is 2, then it's Euclidean distance, okay? If P is 1, then it's Manhattan distance. And over here, like I said, in sklearn, okay, in sklearn, there are many other distance matrix we can choose, okay? So you can refer the sklearn official document to find the definition. Okay, so that's regarding matrix distance. And K nearest neighbor. So next, what it discusses is it is susceptible to overfitting. Okay, and here it says due to it says a curse of dimensionality. Okay, so this is a term also. Let's just try to remember, okay, in machine learning, that's curse of dimensionality. So what is curse of dimensionality? It says describes some phenomena where the feature space becomes increasingly sparse for an increasing number of dimensions of fixed training data set. Okay, so your training, so the number of samples, the number is fixed, but you include a lot of features. Okay, so too many features you considered for the training, for the model learning, etc. And this can cause curse of dimensionality. Okay, dimensionality. And then how do we deal with this? Is it? And here says intuitive, we can also think of even the closest neighbor being too far in high dimensional space. Is it? So if you have too many features considered, okay. And over here, previous we learned is a regularization, regression, ingredient descent, is it can avoid overfitting, is it? Because you penalize the weight, is it? Because we add that extra term. Is that we add the extra term to penalize the weights, is it? And so that's for regularization, but that won't work here, is it? Because here we don't have any discriminative function, is it? So regularization also for decision tree, previously we also learned, is it? And the KNN, regularization won't work, is it? So the way to deal with this curse of dimensionality is through, we call it feature selection, okay, and dimensionality reduction, okay, can help us to prevent curse of dimensionality, okay. So it's, you have too many features, is it, that can cause curse of dimensionality, is it? So if you limited features, you select the best feature that will work for your model, is it? So that can help to better train the model. And the other method is called dimensionality reduction. Okay, so later on we will also see. And regarding feature selection, I'm not sure if you still remember. You remember when we learned decision trees and the random forest, is it? Over there, we mentioned something. You remember we do the bar plotting, and who still remember what that bar plotting is regarding? Do you still remember? It's regarding what? Features. Is it feature importance? Is it feature importance? So use feature importance. So feature importance can help do feature selection. Okay, so this is regarding, because when we discuss machine learning, it's just, oh, you know the model, that's not it. You also need to think about overfitting, underfitting, is it? We call it parameter tuning, is it? To make, because a lot of time the parameters also plays an important role, is it? And over here we also see is a feature selection, dimensionality reduction, is it? And also plays a role, okay? So this is regarding over here, that's a kind of just repeat the previous slide. So over here we have already learned a number of the machine learning models, is it? So let's just take some brief comparison, is it? And here it says different machine learning used to tackle linear and non-linear problems. Is it? We saw that, is it? Like for SVM, support vector machine, is it? If you use kernel one, they can deal with non-linear problems, is it? And the decision tree, so over here it lists each of the ones advantage and in what kind of scenario you can choose to use the model. For decision tree, is it? So if you want to know a lot of detailed decision making, is it? Internal decision making, is it? Then it's regarding interpretability, is it? Then decision tree, remember, you can have that graph, is it? The decision trees graph, and each node, you can get some detailed information, is it? So if you care about interpretability, is it a lot, then you can choose a decision tree, is it? And the logistic regression is that it's not only just a useful model for online learning, is it? Online learning means what? We have learned we can do batch learning, is it? Batch processing. Batch processing is what? So each time you need to, each iteration, you need to have all of the samples loaded, is it? But sometimes that's not feasible, is it? When we do the weight updates, is it? So that's not work if you do batch, is it? So that's why we can do stochastic gradient descent, is it? Stochastic gradient descent is, it doesn't require all of the model, all of the samples, okay? So not all samples, is it, needed at one time, is it? So each sample, you can do also mini batch, is it? So that's called online learning, is it? So it says logistic, it's because logistic gradient descent, is it? Also, we can also choose a stochastic gradient descent with logistic regression, is it? And logistic regression is not just to stop there, is it? It also gives you what? The probability of a particular event, is it? You not just do the classification, is it? It's this class or not. It also gives you the probability of it belongs to that class, is it? And support vector machine, it's powerful linear model, as we know that. And via kernel trick, is it? You can also deal with non-linear problems, is it? And there are many parameters also you need to be tuned, is it, for SVM. Okay, so just be careful. And the ensemble method that we learned, one of it is random forest, is it? A random forest, it doesn't require a lot of parameter tuning, is it? And it's not easy to overfit, is it? Because it's average number of trees, is it? So here it says that's why to make them more attractive, okay? And today we also learn K nearest neighbor, is it? So KNN, is it? So KNN is what? It's lazy learning, is it? And it allows to make a prediction without any model training, is it? But it's memory based, is it? So it's computational expensive, is it? Especially with the storage, is it? So this is a brief comparison, okay? So we are done with the concept about KNN. And next, let's take a look at the example, okay? Example is here. Okay, so this is our example. So for this example, the data set is about breast cancer from the Wisconsin data. Okay, so what over here we have is you load the data and then we take a glimpse of the data, is it? So it has some ID, and then the features, is it? So it has quite a number of features. And then it does the classification, is it, if it is or not, is it? And over here it also does some data cleaning work, because in the original data, if we take a closer look, someplace it may have some question mark, not numbers. Is it in that case, we are going to replace it with some very large number, negative a large number, is it? And over here, that's because we are also going to drop the ID because it doesn't do anything, contribute anything to the model. Okay, it's just some ID, is it? So we're going to drop the first column. Okay, so the data clean, after clean, it looks something like this, is it? And the last column is regarding the class, is it? So that's our target, is it? That's the target. And all of your features is from the first column to the second last column, is it? And then we are going to do the test and train split with 80% to the training data, is it? But here it involves another concept called cross-validation. Okay, so anyway, later on I'm going to explain this. So for this example, we are also going to do cross validation. Okay, and after you get your training data and the testing data, is it? Then we are going to create the KNN model. So KNN is K neighbors classify. Okay, so you just get this model from sklearn. Okay, so sklearn support this model. And you have this model, and then you do the training, is it? And we collect the score. The score looks quite good. It's 98%. And what the next part is just shows we already know this. Is it confusion matrix? Is it? Because over here we only have two classes. Is it breast cancer or not? Is it? So that's why you only have 2 by 2 confusion matrix. Okay, and what the next part shows is a classification report. Is it? Over here you can get a precision recall F1 score. Is it? Of those detailed information. Okay, so you can see it's not a very comprehensive over here. But what the next one try to show is, you remember with KNN, so that number of neighbors, is it? So what's the best number for that? So that takes some training, that takes some comparison also. So what over here is try to do is it try to let the K be, so you have 1 neighbor, 2 neighbors, 3 neighbor, all the way to 40 neighbor. So that's your K number. Okay, and then, so how do we specify the number of neighbors? Then you can assign the n neighbors parameter with some specified number, okay, when you initialize the KNN object, is it? And then you can do fit, you can do predict, is it? Then you can find the arrow, they can find the arrow. And what is the next part try to show is we do the plot of the arrow. Is it the plot of the regarding the arrow and the number of neighbors? Okay, so what's the relationship between the arrow rate and the number of neighbors? Okay, we do this plotting. So the plotting result shows like this. Is it? So we can see through, so neighbors, is it increase from 1 all the way to 40, and here is the mean arrow rate, is it? And we can see it's not that the more neighbors the better, is it? Because from this plotting you can clearly see, is it, after it reach a certain number of the K value, is it, it's basically okay, I'm sorry, I got it messed up here. Yeah, so of course, the more neighbors, the better, but is it, the question is it necessary? Is it, because over here, it's the arrow rate, is it arrow rate? So from this plotting, you can see the K numbers around 20, it's already quite stable, is it? And the arrow rate is also low. and it's also quite stable. So after you do this kind of comparison, etc., then you can pick the optimum K number, okay, for your model, okay. So this is regarding KNN. And what next one is shows our random forest. Previous unit, we already learned the random forest, etc. And over here, let's just take a quick look. Okay, what does it mean over here? So over here for this same set of sample data is regarding breast cancer, is that we also try to do a random forest, okay? And here you're going to use 25 decision trees, is it? And this is each type can do can process 2, is it? So this number of jobs can expedite your processing, make use of multi-core, is it? And then you do fit and you do predict, and you can also collect the accuracy score and the confusion matrix, classification report. It's similar. We can see the result. It's similar. It's 97. The KNN is 98. Is it? And then what the next one try to show is feature importance. In the previous unit, we also we also looked at the feature importance. Okay, so let's take a look in this scenario, is it? So here we list all of the features, is it? In this case, of the features. Okay, we have how many? 1, 2, 3. We have about 3, 6, 9. We have about 9 features, is it? Yeah, so feature labels, and with random forest, is it? There is a parameter that you can pick. Is called the feature importance, is it? So with the feature importance, so after you do the model training, you can collect this feature importance. And over here, we rearrange the feature importance in descending order, that in descending order. And we are going to collect their indexes, that their indexes, so that with the original importance, is it? So that's the importance percentage, is it? And then you know it's index, is it? So we can output of the importance in the descending order, is it? Then in this case, you can kind of get some idea. Is it like the first 2, is it? Takes quite a percentage ratio in the contribution of the model as a feature importance, is it's quite a lot. And for the last one, you can see the percentage is quite low, is it? It's even less than 1%, is it? So a lot of time you can use, so because over here it's discuss feature importance, is it? Feature importance. And we said with KNN, is it? And decision tree, is it? And you cannot use regularization, is it? To reduce the curse of dimensionality, is it? Curse of dimensionality, is it? So the way to get around, like sometimes the overfitting problem, because it's easy to lead to overfitting, okay, with KNN also, and the decision tree, is it? So the way to do it, you can use this feature importance, is that we call it feature selection. Is it? You select a feature, is it? One of the way to do feature selection is you use this feature importance. Is it? You collect the data regarding feature importance, then you can exclude some feature next time when you do the model training, is it? And see the result, okay? So here it shows us, okay, you can directly with random forest collect feature importance, okay. Then you can rearrange, is it in ascending or descending order, then you can find the important feature, okay. And over here it also shows that, so this also used quite a lot, is that you can draw the bar regarding feature importance, is that regarding feature importance. So it's very obvious, then you can see the contribution. And with random forest over here it shows, because random forest you have a number of trees. In this case we have 25 trees, is it? So you remember for decision tree, we can also visualize the tree, is it? Get each individual tree, is it? Get each individual tree. So with random forest, you can also select a tree, pull out the tree from the forest. So here it shows, you can call, it's called estimators. Okay, then you can specify which tree you want to take a look, is it? So here it shows the 6th tree. The 6th tree, and then we can do that tree diagram export, that we discussed that, and then you're going to have that single decision tree, okay, so that you can also know some intermediate decisions, okay. So that's regarding this example. And what next one? Let's show. Because in our example, we mentioned a concept that's also used quite a lot in machine learning. It's, you remember we mentioned cross-validation, the cross-validation. So what is that? Okay, cross-validation. And generally we know is that you have original data set, is that, and you split it into training part and the test part, is it? And then after you do that, you can do the prediction, is it? And over here, is after you do the training, is it? And over here says you retrain the model. You retrain the model with what? And over here it says you do the cross validation, is it? So previously, generally speaking, what we learned is after you do training, you directly do predict, that you can do predict, that, and over here is you can retrain the model, that retrain the model is what? It uses cross-validation concept, okay, and cross-validation, the purpose is to what? Is to find the best parameter, okay, so its goal is to do parameter tuning. Okay, so that you can pick the best parameter, okay? Then you can retrain the model, okay? Then you can do final evaluation, okay? So that's what cross-validation is purpose. So what does that mean? Okay, all of this means, let's take a look. And previously, you remember, like when we do gradient descent, is it, and SVM, is it? If you recall, is it for the sklearn, is it? We have that C parameter, is it? C is what? Is of a lambda, is inverse of lambda, is it? And the lambda is for the regularization. Is it? A regularization is a cost function, is it? Plus lambda sigma and W I square, is it? So all of the weights square, is it? And I already mentioned the purpose is to what? To penalize the weight, is it? Penalize certain weight so that a certain weight won't take too much important role, is it? So that's the point, is it? For that C. That C, we call it what? Hyperparameters in machine learning, okay, hyperparameters. So when you read the article, you see those kind of word, you know what it means, okay. Here it says there's still risk of overfitting on the test set. So even though you train the C, is it with original training data set? So that training data set, is it? And it says still risk overfitting the testing set, okay, because it says parameter can be tweaked until the estimator performs optimally, is it? And then it will lead to what? Overfitting, is it? So I don't know if you still remember the basic concept about overfitting. Overfitting is what? Is due to what? Due to high variance, is it? What does that mean? That means it fit well in training model, is it? But when you do prediction, then it doesn't give very good prediction result, is it? So that's called overfit, okay? As it's leak into the model, evaluation matrix no longer report because it doesn't give generalization performance. Is it performance? Yeah, so to solve this kind of problem, is it? What we can do is, if we can reserve some part of training data set, we hold them out, and we call that part of data validation set. Okay, and the training proceed on the training set. And after that, evaluation is going to be done on the validation set. Then it's going to improve the overall performance, okay? So that's what this general cross validation mean, okay? But the question, how do we partition our data, is it? So when we consider cross validation, so you will see this a lot in machine learning, it's a CV, okay? So it means cross validation, okay? And a very common one you will see, it's, we call it a K-folder cross validation, okay? And with cross validation, then all of the data will be in 3 sets, okay, in 3 sets. So you have training set, okay? And then you also have what? You also have validation set. And the last one is what? Is testing set, etc. So that's what we mean, 3 sets, okay? And but here, what does a K-folder cross validation mean? Okay, so let's take a look. So what it means is, let's take a look at this diagram that makes more sense, okay? So over here you see, the very top, is it, that's your sample space. Is a sample space. And you remember in sklearn, you have that train test split, is it, with a certain percentage, 80%, is it 70%, something, is it? So you have this 2 part, is it, training and the testing, is it, 2 part. So with cross validation, the K-fold. Okay, so you're going to split the training data into certain number of folds, so subset, is it? So over here we have 5 folds, okay, 5 folds. And then in the next one, what we see is we are going to have 5 splits, okay, 5 splits. What does this mean? You're going to, for each fold, each of the fold, you're going to reserve it as validation. So the this blue block means validation set. Okay, all of the green ones means the training. Okay, and so in order to, because if you just always pick a folder 1, that can also lead into make the model leaning toward a certain situation, etc. So that's not good. So that's why you are going to consider all of the folds to the validation set. So that's why we need also, in this case, 5 splits. Okay, so that all 5 folds will be also put as a validation set. Okay, and of the remaining folds will be in the training set. And then with all these splits, you can find the optimal parameters, etc., like C, etc. And you remember we also have gamma, etc. So those parameters, etc., you can find the best parameter. And once you find the best parameter, etc., and then you can do final evaluation with testing of the data. Okay, so this is a general idea regarding cross-validation, okay? And if you let's go back. So in this example, is it in this Wisconsin one, the breast cancer one, is it over here, is it we use cross-validation. Is it cross-validation? Okay. So in order to do that, you can import cross-validation. Is it cross? And then you can go ahead to use it. Okay. So this is the general idea about the KNN, okay, and some other side topic like the cross validation. So that's all of the information for today. Any other questions do you have?